All right, my friends, if you were not sure what to do with D or E, super duper duper understandable. So here's one tip that I want to give you, and it's something that I think will help you as we go through the whole chapter. So a tip. I'm pretty sure I can say this, the only infinite sums that we can evaluate exactly, let's say in this unit, between section 8.1 and 8.6, the only infinite sums that we can evaluate exactly are geometric and telescoping. After these two types, we'd be able to say if it converges, like whether it adds up to something finite, and we might be able to approximate the answer, but we wouldn't be able to get it exactly, okay? So the reason I'm telling you that now is because notice the direction said, if it converges, find its value. So that means that if you suspect that something converges, then it's either going to be geometric or telescoping. So for part D, if you were to start expanding the terms out, I personally don't really care to, but if you did, you'd notice pretty quickly that this is not geometric. If you were to, for part D, if you were to figure out, well, what do the terms go to, right? Like if you were to start expanding it, right? Like at the tail end, what are you adding? Well, I think that you'd find that at the tail end, you're adding a bunch of 4s. So let's check that out. What's the limit as n approaches infinity of 4n squared over n times n minus 2? Well, notice that on the top, you've got degree 2. On the bottom, if you multiplied it out, you could see that you have degree 2. And so your value would be your leading coefficient of the numerator divided by your leading coefficient of the denominator, which is 4. And what's so great or so awful about 4, depending on how you look at it? Well, 4, my friends, is not 0. So that means when you expand it out, you basically have who cares plus who cares plus who cares, because at the tail end, you're adding up infinitely many 4s. So could this thing possibly add up to something finite? I say no. As a matter of fact, I can tell you for sure it'll add up to positive infinity. So I would say for part D that it diverges to infinity. And how do we know that it diverges? By the, nth term test for divergence. Okay. Now for part E. If you check to see what the terms go to for part E, you will find out that the terms do go to 0. So what does that mean? That means you have who cares plus who cares plus who cares. And at the tail end, you're adding up infinitely many terms that have basically approached 0. So what does that mean? That's right. It means absolutely nothing. Just because your terms go to 0 doesn't mean they went to 0 fast enough. So we're going to have to try something else because the nth term test will not help us at all here. So instead, since the thing in the bubble says the only infinite sums that we can evaluate exactly are geometric and telescoping, and if you start expanding this out, you're going to see it's super not geometric. And it doesn't look telescoping either, but a little partial fraction decomposition on the way the terms are defined would actually help you to see that this is a telescoping series. So that's what we're going to do. We're going to take 4 over n times n plus 2, set up the form, There we go. And so then you can rewrite the sum. So this would be the sum as n goes from 5 to infinity of 2 over n minus 2 over n plus 2. Then follow if in doubt, expand it out. Always with telescoping, start expanding it out. So what would we have? We'd have 2/5 minus 2/7 plus 2/6 minus 2/8. And you're going to expand it out as far as you need to until you are absolutely sure that you know what the answer is going to be. I'll move this stuff out of the way. Okay, that was plugging 6 in. Let's plug 7 in. 2/7. Oops, minus that is. 2/9. 2/8 minus 2/10. I'm going to go ahead and show a couple more. I think that should be plenty. And then I'm just going to say plus dot, dot, dot. You can always tell it's telescoping because you'll have one fraction being subtracted from another one in there. And then as far as how many terms you need to expand, it kind of has to do with the difference between these two values there. So watch and see if you can make sense of that as we go. All right, so is the 2/5 going to stay or get kind of canceled out with something? I say the 2/5 stays. The negative 2/7, notice I have to go down 2 expressions to get it to cancel out. Same thing, 2/6 is going to stay. 2/8, I have to go down 2 expressions to get it to cancel out. 2/9 would go away. 2/10 would also cancel out with something I haven't written yet, but is implied in the dot, dot, dot. And the same thing with the negative 2/11. So, and at the tail end, you do have 2 terms at the very end that also did not cancel out, but they approach 0 anyway. So your final answer would basically be 2/5 plus 2/6, or 1/3. There we go. And so you'd have, let's see, what would that be? 6 plus 5 over 15. So your final answer would be 11/15. Congratulations if you got that without my help. There we go. Okay, so at this point, I hope you feel comfortable knowing when a series converges or diverges if it's geometric. You know how to evaluate it if it's geometric. You can tell kind of by the look of a series if there's a potential for it to be telescoping, even if it needs some partial fraction decomposition help. And you can tell when to use the nth term test, for divergence and how to not use that one as well. Okay, so the last thing that I want to do here is make sure you're very clear on why we say the harmonic series diverges to infinity. So for this explanation, what you can do is start expanding the terms and really go to town on it. So it looks like this: 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And then I'm going to start kind of using some plus dot 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 notation. And here's what it would look like. Okay. Plus 1/9 plus dot 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 plus 1/16 plus 1/17 plus dot 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 plus 1 over 32 plus, and I think at that point we'll just go ahead and say plus dot dot dot. Okay, so you start by really going to town on expanding it. And then I'm going to group it strategically. So 1 plus 1/2, and then I'm going to group 1/3 and 1/4 together. And then I'm going to group 1/5, 1/6, 1/7, and 1/8 together. And then I'm going to group 1/9 all the way out to 1/16, and then 1/17 all the way out to 1/32. And I could keep going in that manner forever and ever and ever. But now let me kind of tell you what I'm up to. So for the next step, I want you to kind of note that both 1/3 and 1/4, both of those are greater than or equal to 1/4. I'm going to say that again. Both 1/3 and 1/4 are greater than or equal to 1/4, which means that when you add them together, you're going to get something that's greater than or equal to 2 times 1/4, or 1/2. And then notice in the next group, I grouped 4 terms. And each of those 4 terms, 1/5, 1/6, 1/7, and 1/8, each of those 4 terms is greater than or equal to 1/8. And I have 4 of them. So the sum would be greater than or equal to 4 1/8. And notice that that's also 1/2. And so the argument that I'm going to use here is that I can keep going out and getting enough numbers to add up to something that's greater than or equal to 1/2. So how many numbers did I have to go out to get the next group? Well, I had to go out 8 numbers. So there's 8 values here. And each of them is greater than or equal to 1/16. So these numbers would add up to something greater than or equal to 1/2. And these numbers, and there are 16 of them, each of them is greater than or equal to 1/32. And how far would I have to go out to get my next sum that adds up to be greater than or equal to 1/2? Well, I'd have to go out 32 values. Then I'd have to go out 64. And then I'd have to go out 128. But since there's infinitely many of them, I could always go out far enough to get another value that adds up to be greater than or equal to 1/2. So that means that this would equal, or that this would be greater than or equal to 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 forever. I could always go far enough out to get something that adds up to be bigger than 1/2. So this would approach infinity, and it actually approaches infinity in a way by the nth term test for divergence. Anyway, even though the terms did go to 0, okay? So the summary is that, and we're going to keep this in our back pocket to remind ourselves, keep ourselves out of trouble. The harmonic series diverges to infinity. Even though its terms approached 0. There we go. All right, my friends, try to remember about that harmonic series. It'll keep us out of trouble later. Take care, everybody.